Beneath a shell of ice so smooth it reflects the dim light of a distant sun, something moves. Not a rumor, not a metaphor. An ocean, liquid, vast, and almost certainly in contact with a rocky seafloor, has been churning for billions of years on a moon smaller than Earth's own. The question that follows is not whether that ocean exists. The instruments have settled that. The question is what that ocean means, and what it would take to find out. Europa is the second of Jupiter's 4 large Galilean moons in orbital distance from the planet. It is slightly smaller and less massive than Earth's moon, close enough to Jupiter that tidal forces knead its interior continuously. Those forces generate heat. That heat keeps water liquid at a depth where sunlight has never reached and never will. Europa was first observed as a distinct body on January 8, 1610, when Galileo Galilei resolved it from the glare of Io using a refracting telescope of roughly 20 magnifications at the University of Padua. For the next 3.5 centuries, it was a point of light. Only space-age instruments would reveal what that point of light was hiding. What those instruments found rewrites the basic arithmetic of habitability. Europa's surface is unlike almost anything else in the solar system. It carries almost no large craters, striking for a world embedded in the Jupiter system where impactors are abundant. The crust is fractured by long reddish-brown streaks and crisscrossing ridges, but the relief is extraordinarily low. Europa is, according to available measurements, the smoothest known solid object in the solar system. That smoothness is not inert, it is a symptom. The surface is geologically young, meaning that whatever formed most of its visible features did so relatively recently in planetary time. The leading model holds that a subsurface ocean of liquid water lies beneath the ice, that tidal heating drives convective motion in that ice, and that material circulates between surface and ocean in a process that resembles, in some ways, the plate tectonics that recycles Earth's crust. The expectation going into the Galileo mission, launched in 1989 and operational around Jupiter from 1995 to 2003, was that Jupiter's icy moons would be geologically dead. Frozen, cratered, and inert. That was the prediction for worlds so far from the Sun that surface temperatures sit around -160 degrees Celsius. Europa rejected that prediction comprehensively. Galileo's magnetometer detected a magnetic signature consistent with a conducting fluid beneath the surface, a subsurface layer that interacts with Jupiter's powerful magnetic field in a way that solid ice simply cannot replicate. The inference from that measurement, which remains the most cited line of evidence for the ocean, is that a saltwater layer of substantial depth exists beneath the crust. Galileo's data also returned imagery of surface features consistent with material that had been disrupted, refrozen, and disrupted again, a pattern more consistent with mobile ice over liquid than with a static, frozen body. Then came the plumes. The Hubble Space Telescope detected water vapor above Europa's surface in observations interpreted as possible cryogeyser activity, eruptions of water or water vapor from the interior. In May 2018, researchers publishing an updated analysis of Galileo flyby data provided supporting evidence. The probe may have flown directly through a plume during one of its close passes, without scientists recognizing it at the time. The instruments were not designed with plume detection as a primary objective, so the signal sat in the data for years before the reanalysis surfaced it. If confirmed, plumes would be profoundly significant. They would mean that material from the subsurface ocean is reaching the surface, and potentially beyond it, without requiring any spacecraft to drill through kilometers of ice. Europa also carries a thin oxygen atmosphere. It is far too tenuous to breathe. generated not by biology, but by radiation-splitting water molecules at the surface. But the presence of oxygen at the surface raises a structural question for habitability. How much of that surface-generated oxidant reaches the ocean below? If Europa's ice recycling mechanism transports oxidants downward, the ocean could receive a steady chemical energy supply, the kind of redox gradient that powers life in Earth's deep-sea hydrothermal systems. Sea salt observed coating some of Europa's geological features suggests the ocean is indeed interacting with the seafloor, not sitting as a chemically isolated layer. That seafloor interaction matters. On Earth, the chemistry at the boundary between rock and ocean is where some of the most ancient and resilient life forms operate. In March 2024, however, astronomers reported a significant revision. Analysis suggested that the surface of Europa may contain substantially less oxygen than previous estimates assumed. That finding does not eliminate the habitability hypothesis, but it constrains it. The amount of oxidant available to cycle downward into the ocean may be lower than models that used older oxygen estimates had predicted. The revision illustrates the core difficulty of studying Europa from a distance. The Moon's most important processes happen beneath a surface we have never touched, and every number derived from remote sensing carries measurement limits that can shift an entire framework when they are refined. The instruments used span decades and methods. Pioneer 10 and 11 in the early 1970s provided the first spacecraft views, but resolution was low. Voyager flybys in 1979 revealed the fractured surface in detail sufficient to recognize its youth. Galileo, with its magnetometer, near-infrared mapping spectrometer, and imaging system, produced the bulk of the close-range data that drives current models. In September 2022, the Juno spacecraft executed a flyby within approximately 320 kilometers of Europa's surface, providing updated close-up imagery. The European Space Agency's Jupiter Icy Moons Explorer, launched in April 2023, is en route to the Jovian system with 2 Europa flybys planned. NASA's Europa Clipper, launched in October 2024, is the most capable Europa mission ever flown. Its instrument suite includes radar designed to probe the ice shell's thickness and structure, a magnetometer to characterize the ocean's depth and salinity with far greater precision than Galileo achieved, mass spectrometers to sample any plume material, and cameras with resolution substantially exceeding the Galileo baseline. Current evidence supports a ranking of competing explanations for Europa's habitability potential. The leading hypothesis, supported by the magnetic field anomaly, the surface geology, and the sea salt observations, is that a liquid saltwater ocean exists beneath the ice and is in chemical contact with a silicate seafloor. This is not a fringe position. It represents the mainstream interpretation of the available data. A secondary hypothesis holds that the apparent ocean signature could reflect a layer of brine-saturated ice rather than a true liquid ocean, a distinction with significant consequences for habitability, since a brine layer would constrain both volume and chemistry. The plume detections, if confirmed at higher confidence, would argue against a fully frozen intermediate layer and support true liquid at accessible depths. What Europa Clipper's radar returns will be decisive. If the ice shell thickness comes in at the lower end of current estimates, perhaps a few kilometers rather than tens of kilometers, it strengthens the case that surface oxidants could cycle into the ocean on geologically short timescales. If the magnetometer data refines the ocean's salt concentration, it will constrain whether the chemistry resembles Earth's ocean closely enough to sustain the metabolic pathways we understand. If a plume is sampled directly, the mass spectrometer results could, in principle, detect organic molecules or chemical disequilibrium of the kind that biology produces on Earth. None of those findings would prove life, but any of them could falsify the leading habitability model or elevate it past its current threshold of supported inference. What Europa has already changed is the map of where to look. Before Galileo's magnetometer returned its data, the only world assumed to hold a liquid water ocean was Earth. Now the solar system is understood to contain multiple ocean worlds: Europa, Enceladus at Saturn, possibly Ganymede and Callisto, possibly Titan beneath its hydrocarbon surface. Europa remains the most studied of these because it combines the right ingredients in measurable proximity: liquid water, a rocky seafloor, chemical energy from tidal heating, and a mechanism that may deliver surface oxidants to the deep. Every one of those ingredients is inferred, not directly sampled. But inference built from independent lines of evidence, magnetic, geological, spectroscopic, and now possibly plume-based, is how planetary science advances before a lander ever touches the ground. The ocean beneath Europa's ice has been there, by most estimates, for the age of the solar system. Whether anything has used that time is the question Europa Clipper is now traveling to help answer.